Hello and welcome to our ANSI C89 presentation. I'm Andrew Nguyen and I'm joined by my group members, Justin Nguyen and Nathan Huang. And today we will be presenting our compiler in 4 sections. To start off with lexical analysis, I'll turn it over to my team member, Justin.
Hi, my name is Justin, and I'll be explaining the implementation of the lexical analysis. We leverage the JLEX to parse tokens, terminals, and non-terminals from our source code files. We work to define context-free grammars to account for all possible ANSI C89 non-terminals. We also implemented multiple states to account for parsing comments and strings from the source code files. To demo, we will run our lexical analyzer with driver code to print all parsed tokens and non-terminals.
All right, so taking a look at our source code, these are just typically some terminals that you would see in your average file. When we run the lexical analyzer, you'll see these parsed as tokens with respective IDs. Okay. And as you can see, it generated a stream of different tokens, and those are just the token IDs next to those as well. Moving on to parse tree generation. All right, so for parse tree generation, we leverage Java Cup to define different grammar rules that would then generate a parser. That would build a parse tree from tokenized input produced by our Lexer. All right, and so to demo this parse tree generation, we're going to be printing our abstract parse tree in the terminal where the tree hierarchy is represented by different tab spaces. Okay, and so looking at uh, the source code for our demo, these are just some standard function definitions that would be in a C89 file. And as you can see for our generated parse tree, different tabs would just coincide with the level within the parse tree that each element is. And yeah, and moving on to our semantic analysis and the implementation of activation records, I'm going to turn it over to Nathan Huang.
Hi, I'm Nathan. So we implemented a semantic analyzer for our compiler, and what this analyzer traverses the abstract syntax tree to perform type checking, scope resolution, um, forcing language semantics such as declaration validation, return type and parameter matching, as well as struct and array usage. And we also simulated activation records by assigning memory locations to function parameters and modeling the stack layout using a structure that stored access level info. And upon any violations of the parser will store caught errors. And for the purpose of the demo, any caught errors are rendered in the terminal. We will first we will first demo the semantic analysis on a valid source code and introduce invalid code to demonstrate the analyzer's ability to catch errors.
Okay, so we're firstly going to demo our semantic analysis on valid code to start. And so as you can see, uh, this is our test. This function that we're moving is our test block for invalid code, but all other code within the source code is valid for this run. All right, and so yeah, so no errors are caught there. Let's go ahead and bring back that invalid code block. All right, and just looking through some of the invalid test cases, you can see we passed invalid function arguments. Maybe we called functions that didn't exist or return types that were invalid to the definition of the function, or also just attempting to call an integer as a struct. You can see some of the errors that we were able to catch and return here in the terminal. All right, moving on to the intermediate code tree generation and instruction code selection section. So we integrated a frame-aware translator into the existing semantic analyzer in order to build procedure frames and manage static links. We also implemented all the transition hooks for every possible abstract tree node that we could run across during our semantic analysis, and we lowered them into the canonical tree intermediate representation so that they can be printed and further optimized. For our demo today, we will just be generating an intermediate code tree for a simple function definition using the included driver code that integrates the semantic analyzer with the translator. Alright, so to begin our demo, taking a look at the source code that we're going to be translating today, it's just a simple function definition. Let's go ahead and generate a intermediate code tree for this. Alright. Alright, and if you take a look at the terminal, we were able to generate an intermediate code tree for that. And yep, moving on to the final section. In the final section of our presentation, we want to address some limitations and shortcomings that we had across each implementation of the sections. For our lexical analysis, we felt that we were able to deliver a competent lexical analyzer that was able to parse source code files and allow us to build upon that within each of the following projects. For parse tree generation, this is the one that we felt that we faced the greatest difficulty in implementing because we had split the project progress up between group members, and during the time to actually combine the work, it became very difficult, and we ran into many compile time and runtime errors whenever we were using the parse tree generator. And so in order to implement a working version, we did have to reduce a lot of the functionality just so that we were able to get everybody's work integrated within one solution. Following that project, though, we were able to modify the skeleton code in order to generate a more competent parse tree generator for use in the following projects. All right, and for semantic analysis and activation records, we were not able to implement nested array validation, and also for some built-in functions, we did notice that there were some runtime errors in recognizing that the functions do exist for functions such as print or etc. We also were not able to implement escape analysis. For the intermediate code and instruction selection section, we felt that we were able to generate intermediate code tree representation reliably. However, we were not able to fully implement instruction code selection. As it stands, our compiler parses full ANSI C89 source into an abstract syntax tree, performs semantic analysis while simulating activation record layout, and finally lowers the checked program into a canonical intermediate code representation that is ready for code generation.